Hello, everyone. Today I will introduce our work, No Reference Image Quality Assessment using Dynamic Complex Valued Neural Model. As we know, image degradation often occurs due to imperfect imaging systems, recording equipment, transmission media, and processing methods. To measure the perceived image degradation, image quality is evaluated as a characteristic of the image. The goal of objective IQA is to develop a quantitative measure that can predict perceived image quality automatically. And no reference IQA aims to evaluate image quality without assistance of the reference image. It plays an important role in various image processing applications, for testing, optimizing, benchmarking and monitoring. Recently, CNNs-based NR-IQA models have achieved success. However, there still are two aspects to improve the power of CNNs for NR-IQA. Firstly, most existing CNN models for IQA are built upon real-valued operations, while the power of deep complex valued representations has not been exploited in IQA yet. Complex representation are known to have rich representational capacity due to complex numbers. For IQA, the properties of natural images can be easily captured using complex number in terms of local phase. In the view of biological perception in human visual system, some characteristics of responses of the cells in primary visual cortex such as orientation selectivity can be modeled by complex valued transforms. For traditional IQA models, complex transforms such as Gabor transform, discrete Fourier transform have been widely adopted for complex valued quality-aware feature extraction. Besides, phase-related features also have been widely exploited. Motivated by traditional complex valued representation, we introduce deep complex valued representations to IQA. Complex valued convolution can benefit the model compactness via effective size reduction on CNN models compared with real valued convolution. In addition, complex valued convolutions introduce interactions between real and imaginary part. Secondly, a traditional CNN model is typically content agnostic since the standard convolution shares static filters across different pixels and different input images for a trained model. So different image contents with diverse distortions will be processed by the same filters. However, in general, different image contents may be sensitive to different distortions. For example, a flattened area is usually insensitive to blur while a textured area is sensitive to blur. Consider a flattened area. It may be considered a high-quality pattern when it is located in an image of a clear blue sky, while it is regarded as a serious blurring in a textured image. Thus, to construct an ideal IQA model with human consistent quality perception, the content-aware feature extraction by dynamic filters is preferred. And the filters used to extract quality-related features should be related to the image patterns to be analyzed. To break these two limitations and improve the effectiveness of CNN-based NR-IQA, we introduce complex-valued deep learning for NR-IQA to utilize the merits of complex-valued representations. We also introduce the dynamic filtering technique to the complex-valued NN to extract features via dynamic filters conditioned on both the local contents and global semantics for better mimic human perception of visual quality in authentic cases. From experiments, the proposed method outperforms several state-of-the-art methods in most cases. The proposed model consists of a static complex-valued CNN for the pre-stage feature extraction, and a complex-valued dynamic filtering module for content-aware feature extraction. Then, a complex-valued regressor is applied to predict the quality score with extracted complex features. Similar to existing works, the DC-net is combined with a pre-trained backbone for improvement. There are some basic complex valued layers for pre-stage feature extraction. Let X K denote a complex-valued feature map and a complex-valued kernel respectively. Then the complex-valued versions of convolution layers, batch normalization layers, ReLU activation layers and the residual block are defined based on the real-valued ones. To construct complex-valued dynamic filtering module, filters for real part and imaginary part of complex-valued inputs are generated separately, and filters for each part are generated by one real-valued spatial branch and one real-valued channel branch. The spatial branch takes a local receptive field to predict local content-aware filters, and the channel branch takes the whole image as receptive field to predict global semantic-aware filters. For the feature of one joint location on PTH pixel location and JTH channel, the dynamic filtering module generates a complex-valued filters for it. Then complex-valued dynamic filters are applied to complex-valued input of DF module to obtain content-aware features. Finally, the extracted features are transmitted to the complex global average pooling and then are regressed to a quality score by a complex fully connected layer. In order to validate the performance of the proposed method, 6 publicly natural image IQA databases are employed in our experiments. PLCC and SROCC are criteria used to evaluate performance. PLCC measures the linear correlation. SROCC measures the prediction monotonicity. An effective IQA metric is expected to yield high values of PLCC and SROCC. For training, we use the Huber loss due to its stronger robustness to outliers over the commonly used mean square error loss. From performance evaluation on single dataset, it can be seen that the proposed method significantly outperforms the compared methods on 3 synthetically datasets. For authentically data, the proposed method performs significantly better than all compared methods on the large-scale dataset conic 10 kelvins and SPAQ. It is comparative on live C. Note that conic 10 kelvins and SPAQ contain over 10,000 realistically and complexly distorted images, which are usually more challenging for evaluation. To evaluate the generalization ability, we conduct a cross-dataset experiment. The results indicate that the proposed model has a good generalization capability, especially for predicting the quality of pictures of arbitrary resolution and of real-world complex distortions. In order to evaluate the performance on diverse distortion types, we collect the results of CNN-based models on diverse categories of CSIQ. As can be seen, DCNet achieved the best evaluation performance for all types on CSIQ. For direct visualization, a GMAD competition is conducted on the SPAQ database. The GMAD selects image pairs to determine whether the attacker or the defender is robust. From figures, it can be seen that the DCNet correctly attacked HyperNet. When we fix DCNet as the defender, it successfully survived the attack of HyperNet at the low and good quality levels. In addition, it is worth mentioning that both DCNet and HyperNet recognize the obvious low-quality images successfully. To verify the effectiveness of the complex-valued architecture and the dynamic filtering module of DCNet, we conduct ablation studies under several settings. We construct several baseline 1, baseline 2, RealNet and static net of DCNet. Note that the FC layer is used and trained for the first 2 baselines for score regression, and the backbones in both RealNet and static net are not fine-tuned. From the results, we know that each component has a noticeable contribution to the performance of the DCNet. In detail, compared to baseline 1, RealNet and static net obtain gains. Such improvements demonstrated the effectiveness of the complex-valued architecture and dynamic filtering of DCNet, respectively. Compared to baseline 1, The original DC net shows SROCC gain on average, which demonstrates its effectiveness. Compared with RealNet and static net, DC net still achieved approximately additional gain on average. Such improvement comes from the combination of the complex valued architecture and dynamic filtering over the individual ones. Compared to baseline 2, DC net achieved better results, which again demonstrated its effectiveness. DC net with backbone fine-tuning achieved even further improvement on 2 datasets, but showed a certain performance decrease on the Live-C database, which is probably due to overfitting. Indeed, DCNet already performs very well without the time-consuming backbone fine-tuning. Finally, let us conclude our work. We apply deep complex valued representation for NRIQA and apply dynamic filtering for content-aware feature extraction in IQA. In the future, we will investigate other merits of complex valued CNN modules for the improvement of NRIQA and further study connection between complex valued convolution and dynamic filtering. Thanks for your attention.